Hi, we have developed a system for you to test your aluminum's thermal performance on a brake disc under client-specific loading conditions to convince them to use your aluminum and start prototyping. You start with a spreadsheet of parameters. Here, each row describes a specific loading condition for which you need to simulate a braking event and extract maximum temperature, maximum thermal stress, and maximum delta T during the braking event. Back to the dashboard, you can see that our model connects to COMSOL for its physics simulation backend. You start by uploading a brake disc step file, which contains the geometry of the brake disc with the rotor and the pad. You also upload the parametric data that we just saw. Once you hit analysis, our model looks at the geometry and the spreadsheet and starts reasoning. It finds brake disc and brake pad components, and it also looks at the empty columns in the spreadsheet to infer that it needs to run a transient thermal simulation to simulate a braking event. Once it has also seen the parameters in the spreadsheet, it then generates a simulation plan. The plan is to perform a transient thermal analysis to simulate heat generation during braking, model friction, apply convective cooling, analyze temperature distribution and gradients, and then output the maximum temperature, maximum thermal stress, and maximum delta T for each simulation within the spreadsheet columns. If it looks good, you can hit proceed. Our model starts first by identifying and naming different components. In this case, it's brake disc and brake pad. It then applies material properties to each component, defaults to aluminum for the disc and ceramic for the pad. You can change the material properties at any time from up here. It then autonomously identifies faces on which convection needs to happen and then applies convective boundary condition. It then also identifies the surfaces in contact to model friction. Once the boundary conditions and constraints have been added, it then starts meshing. As you can see, the first mesh did not pass the quality checks, and so our model went ahead and performed local refinement to generate a higher quality mesh which passes all the checks. Once the meshing is done, our model then goes ahead and runs the simulation. This is a placeholder simulation result that shows a thermal distribution or temperature distribution where the blue regions are low temperature or indicate low temperature, and the regions that are orange or green indicate higher temperature. Once the first simulation has been run, our model has a template on which it can just tweak variables to run all the simulations in the loop as described in the spreadsheet. All these simulation results are available for you to look at the bottom. The red bar at the bottom indicates mechanical failure, where the maximum temperature exceeded a certain threshold. The yellow ones are the results or the situations where the maximum temperature comes close to failing, and the green ones are the ones that passed. Our model post-processes these results for you and updates the spreadsheet where necessary. You can download the updated spreadsheet from this button. As you can see, our model has added maximum temperature, maximum thermal stress, and maximum delta T for each of the simulation runs required, and now which can be used for design insights. Thank you.